Hi all, this is Mr. Yeager for AP Physics, looking at one additional concept that AP Physics 1 has really decided to emphasize more in the simple harmonic motion unit this year over prior years, especially with a particular equation. Obviously, you saw in prior video me talking about how to kind of interpret looking at simple harmonic motion through graphs. We now have a formula that makes that a little bit clearer. Obviously, you probably recognize many of these graphs as sine graphs, etc. You're going to see that in the formula in terms of being able to actually identify where an object is at all times while it's in simple harmonic motion is what we're looking at here. So, with that, let's go. Okay. So, we have, you can see over on the left, the formulas that have been introduced so far. And when I'm looking at these simple harmonic motion, I am mainly looking at springs. We can look at this with pendulums as well, but the AP test is primarily going to be focusing with spring motion with these equations. So we have the period of a spring. It's 2 pi times the square root of the mass over the spring constant. We also know frequency is the inverse of the period, okay? Or is equal to 1 over the period. Yeah, the inverse of the period, okay? So we have those two formulas, okay? What I want to introduce is omega, and I feel like I say introduce, it's something we've learned already. We know this is angular velocity, but another term for it is angular frequency, basically how quickly it is rotating around and around and around, counting it out. And so what we can do is we can calculate angular frequency by doing 2 pi over the period, okay? And that's useful and important, you'll see with some of the formulas we're about to kind of put out, okay? So there's lots of variations to this formula, okay? Because we know t is equal to 1 over f, or sorry, let me do that again. Let me expand this out. What if I change this to 2 pi times 1 over t? I can see the angular frequency is equal to 2 pi times the frequency. So these are two different types of versions of the same quantity, just in terms of period and in terms of frequency. Now, the other kind of neat thing we can get out of this is where we get these root formulas in our period equations, whether it's springs or it is pendulums, okay? And so what we can do with this, if I play around with it for a second, is we said angular frequency is equal to 2 pi over t, okay? 2 pi over t. Now, I'm going to redo that real fast. If I kind of rearrange this equation, the spring equation on down, I'm going to divide 2 pi to the other side. So I get t over 2 pi equals the square root of m over k. Okay? Well, omega is equal to 2 pi over t. So if I simply inverse the two of these things, you can see that the angular frequency for a spring is equal to root k over m. The angular frequency is equal to root k over m. So you can determine what's given in the formula for the period of a spring is the 1 over angular frequency is what's under the root. Okay? And we can do the same thing with the pendulum formula. Okay? The period of a pendulum is equal to 2 pi times the square root of length over g. What we can do is, again, we get 2p, period of the pendulum over 2 pi equals root L over g. All right, if I take the inverse of these, that's equal to the angular frequency because I flip it, 2 pi over t. And so root g over L is also equal to the angular frequency of a pendulum. Okay, the angular frequency. All right, so all of this is important because it leads to these two formulas that we are now using and emphasizing more in AP Physics. Okay, and these describe very clearly the graphs that are formed with simple harmonic motion functions. Okay, so you can see I have two different ones. We have x equals a cosine 2 pi ft, and x is equal to a sine 2 pi ft. All right, so let's just talk about the formula first a moment. What the formula is telling you is it's actually, this is a formula we can use to determine exactly where an object is during simple harmonic motion while it's moving back and forth. Okay, if I draw a nice little picture. As it's oscillating back and forth, you can find the exact position of the object at any point in time. Okay, as long as you know the frequency and you know the amplitude of the system. Okay, is what we're looking at here. Well, what you hopefully notice is A is going to be amplitude. And part of the questions in these problems you're going to see is you just have to be able to create these equations. A lot of the questions that are on AP Classroom and other things like that is, you know, here's a situation, which of the following equation fits with the situation? So A is amplitude, so if they give you the amplitude, that's at the beginning of the function, okay? And then 2 pi f, that's your angular frequency. So you might may use it as 2 pi f, or this might be written as 2 pi over period times t. Again, you got to be careful here. See, I'm already going to rewrite that. 2 pi over, make this very clear, period times t. Okay. That would be the same formula inside the parentheses. All right. In AP Physics C, we usually just write it as omega t. Okay. When you eventually get it, if you take AP Physics C. Now, why then do I have two different trig functions with this? That depends on where you are starting your problem. Okay? That depends on how you're, like, where are you, when are you starting to look at this oscillating motion? For the cosine function, you are looking at the fact, and I'm going to put this is technically the equilibrium point. The cosine function is representing when the object is at the maximum amplitude at the start of the problem. So the example here would be you push in the spring, that is the, and then release it. You started with the a cosine 2 pi ft formula because you started away from 0 and it's returning back to 0. Okay? So that's where you use the cosine function. The sine function basically is describing the same thing, but is starting the problem at a different time. And for the sine function, you are looking at the point where it is at equilibrium. Okay? So maybe it's already been released and is moving, and you start the timer as it passes through the equilibrium point. That's why it's at 0 at the beginning. All right? These are still distance time, position time functions. So the slope of these lines is still velocity, and that's some of the things that we might be messing around with, is obviously being able to change it to another form. But what I've seen so far with a lot of AP Classroom, and I've seen this in APC, which obviously is very much related to, is just the creation of these functions, where you are given the period, or you have to discern the period by the graph, again, the time for one oscillation. That's what you're trying to put together to create out these formulas. So at least you now know, okay, if I'm starting at the amplitudes, I must pick a cosine function. If this is beginning at the equilibrium position, I start with a sine function. All right. With this, one of the other things we could possibly do is make you try to consider how to change that position function into a velocity function, into an acceleration function. Okay? And so what you need to kind of consider here, let me try to create one. Hopefully I can do this very nicely. Okay? And I'm going to start up here and come down and go up and down and try to go a little farther. I want to finish nice and simple here. Okay. So you can see my function here. We could say that this is technically positive A. I'm going to actually make it 2A. This is positive 2A and this is negative 2A. Okay? And then we could set up our times on this. So this would be t naught, this would be 2t naught, and this would be 3t naught. Okay? All right. And so we have our position time graph here. You can see this would be related to a cosine function. Okay? We could go ahead and actually try to create that. Let's create that. So it would be x equals, what is the amplitude of this? And again, I didn't make it perfect. The idea is it is always going back to 2a and to a. So this would be 2a cosine, parentheses, okay? And I need to do 2 pi f. So if I do, it's going to be 2 pi. I need to figure out the frequency, okay? So how many, I want to figure out when one wave passes. Okay, frequency is waves over time. Wait, no, it's time over wave, sorry, time over wave. See, I do so, no, it's waves over time, period is time over wave, sorry about that. One wave is complete at 2TO. So this would be 1 over 2T naught. That would be my frequency. So that's what I'm going to plug in here, times 1 over 2T naught T. And then technically I can reduce that, the 2's cancel out, so this should actually just be pi over T naught times T. Okay? That would be my position function that I'm creating here. So my angular frequency, if they ask that, would be pi over T naught. Okay? Which makes sense. All right? So, what I'm going to do here is, okay, I want to change this into a velocity time graph. Okay? And so what I need to consider is, and the probably an easy way to kind of see this is think about where the object is at different points in time. If I'm at an amplitude, my object is not moving. Okay? So that's where I am at rest. Okay? So I'm at rest at T naught. And again, you can do that because the instantaneous slope at that time, the instantaneous speed would be 0. At 2T naught, I should be back at 0. Okay, at 3T naught, I should be back at 0. All right? And then the idea is, now the only thing we have to kind of think about is which direction is this going? Which direction is the object going? Well, if you have a downward slope, it should be negative. So what we're seeing here is that we should get a graph that looks like this. Yep. Wait a minute, that's the end there. Just trying to get this right. So I got that, because that would be the maximum speed. That would be the maximum speed between, that would be the maximum speed in between. Yep, okay, yep, and then back up that way. There you go. So you can see what we have going on here, okay? This would be velocity time. The maximum speed should be when it's passing through the equilibrium point. We said that's where it has the maximum kinetic energy, all right? So we basically get this is going to be a negative sine curve, okay, is what we're running into here, but it matches the same motion that the position time graph function is doing as well, all right? And that could be all you kind of do. What I'd really be encouraging is find where the minimums and maximums are, and that's part of what they're going to be asking you to do with this. Find min-max speed, min-max position, all right? And you can kind of do that just by looking at the initial graph. Everything does kind of shift over in terms of time, if you want to look at it that way, in terms of the shape of it. But I would just look at the min and maxes. Now, I'm going to erase this one. What about velocity? Okay. Actually, I don't want to. I'm going to try to do this without erasing it. Okay. What about acceleration time graphs? Okay. And so I have T naught, 2T naught, 3T naught. Okay. Acceleration time graphs. Okay. I can write in here negative V max, positive V max, so you at least recognize where those are occurring. All right. So we can look at this again either from the velocity time, which we know the slope is equal to the acceleration, or we can look at the position time graph. Let's go and do it with the velocity time graph. So again, what I can run into here is, actually I'm going to start with position time. Sorry, I'm jumping a little bit. Where do you have maximum accelerations during an oscillation? The maximum accelerations occur at the max amplitudes, because that's where the greatest amount of force is. At equilibrium, there's no acceleration. So basically, it's going to look very similar to my distance time graph, which is why I wanted to go off of that one first. But it's going to be the opposite, okay? It's going to be the opposite of what's going on with it, okay? So when I'm at the maximum, this would be technically where 2A is, the acceleration is trying to bring it back in the opposite direction. So what I run into is, it should go up and down, sorry. It should go, yeah, we should be a positive there, and then back to negative here, and then positive there. I think that's what we got, right? Yep. All right. and we'd get something like this. Yep, that's what it'd be. It'd basically be the opposite of the position time graph. That's what I wanted to show. But this matches it, again, because we got a negative acceleration and then a positive acceleration after the max velocity point, so we should be crossing 0 right there, and then a positive acceleration, and back and forth and back and forth. All right? So we can then label, obviously, negative A max here. Negative A max is where we're at positive amplitude, and then a positive A max is where I'm at a negative amplitude, because I'm trying to push back toward the positive. So that's what we're looking at with some of these graphs. This part you might need to rewind and kind of look at again to see how I did it a little bit. Okay? So we already kind of did this one. All right, I guess we could try it again, see if this is the exact same one I just did. Okay? But one more time with this, what I would look at, and you get a problem on the test, and maybe it's multiple choice, it goes, okay, create a function for this graph. Since you are starting at a maximum, you know you're doing a cosine equation. So you can eliminate any choices with sine. Okay, that should probably eliminate 2 choices and you're down to 2 left on a multiple choice. The amplitude should be 2x, because that's the max amplitude. Be careful, because if it goes up to 4x but the line doesn't ever reach there, don't say 4x. It's wherever the maximum height of the graph basically is. And then this is exactly like what I have. You need to figure out, where does one wave occur? One wave occurs after a time of t of 2t naught. So I would do 2 pi, frequency is 1 over 2t naught. So I'm going to multiply that, 1 over 2t naught, times t. Again, the 2's cancel out, and so you are left with, at the end here, pi over t naught. T is my function for displacement. Okay? So we're looking at understanding angular frequency, introducing that terminology a little bit more. Okay? This would be the angular frequency of the motion of this particular setup, of this system. We've showed illustrated ways of how to calculate angular frequency, where it's just the inverse of the root in the period formula, okay? And how to basically put together these new trig functions for simple harmonic motion, okay? And how to identify mins and max. That's it. Thank you.